So, entropy and enthalpy both are important to work out whether a reaction is spontaneous or not. By spontaneous, I don't mean, you tend to think of, like, for instance, white phosphorus. If white phosphorus goes dry in the presence of air or oxygen, it will automatically burst into flame. Okay, that's why it's used in bombs, unfortunately, because of that. So a lot of students tend to think of spontaneous as being, it's going to happen, the moment you let it go or something. But in chemistry, what we mean by spontaneous is in the thermodynamical sense. In other words, thermodynamically or theoretically, it is possible that it will work. And the reason why we break it up into two bits is, does anybody not know what activation energy is? You should have come across it in level 1 and level 2, but I just want to check. Does anybody not know? Okay, you know, great. So hopefully the others. So if you think about it, if the energy of your reactants are over here, and the energy of your products could be either higher or lower, okay? However, to get from reactants to products, there's like this energy hump. So for some reactions, it needs a lot of energy to form the intermediate before it will form the products. In others, it will hardly need any energy to form the intermediate to get to the product. So in chemistry, we call that the kinetics. And so we can have something that's, the reactants have very high energy and the products very low energy. So thermodynamically, it's very possible because these are big drop in energy, so it should happen. But if the energy hump to get there is too big, if the activation energy needed is too big, it's not going to happen unless you increase the temperature. So the energy hump or activation energy is all to do with kinetics, how fast a reaction happens. What we're going to be concerned with is the thermodynamics. We're just looking at the difference between the products or the reactants and the products. So it could be higher or lower, but we're looking at that difference. So when we talk about a spontaneous reaction, we're saying that theoretically that reaction is possible. Okay, so don't think of spontaneous as being something that's just will happen, Okay, right, so for a reaction to be spontaneous, if that's now clear, we need to think of both the enthalpy. Enthalpy is just a fancy name for heat. So think of heat energy. If it's associated with a reaction, it gets given the fancy name of enthalpy. Entropy is the dispersion of energy and matter. And the easiest way to think of it is to think of disorder. Okay, how disordered is a system? Because from the second law of thermodynamics, the whole universe is going into more and more disorder. That is the driving force. And in a chemistry reaction, that's the driving force. So the more disordered it is, the more it's going to go that way. So that's the first thing. You need a positive change. Now, I know your parents won't like it to be a positive change if you make your room very, very disordered, but that's the way it goes in chemistry. So the more disordered you make your room, the more positive it is. So the more positive the change, the more disordered it becomes, and therefore it'll be spontaneous. So let's, so what I've got here is that the change in entropy, and I will explain what entropy is just now, overall must be a positive change. So there must be an increase in energy, increase in entropy, an increase in disorder. Okay, so let's see how this is going to work out in terms of how does heat relate to entropy, because I said entropy is actually the dispersal of matter and energy. If I drop my temperature, then you should know the kinetic energy of the particles will what? Increase or decrease if the temperature drops? So some of you are typing. It'll decrease because everything slows down. And if things are slowing down, can you see there's going to be more of an order coming into the system? Because they'll start, the intermolecular force of attraction will start putting them into particular spaces until you've cooled it down so much that they're now solids and in a particular order. So just to check that you got the right idea, what has more disorder, a gas or a solid? A gas has more disorder. Okay, a solid has more order, so it's got less entropy. Okay, if you increase the temperature, you're increasing the kinetic energy. So everything is whizzing around a lot faster and going everywhere. Solids are breaking up and so on and so forth. There's more disorder, and so there's an increase in entropy. So that's why I think it's a nice concept to think of it in terms of order. But as I say, in terms of the correct definition of dispersal of matter and energy, can you see if your particles are whizzing around much faster, going everywhere? Can you see you dispersing particles in all different spaces, and they're whizzing around, so the energy is being dispersed further? So that's the idea. And if things are getting more ordered, matter is going more in one place, it's less spread out, and the energy is less. So, okay. Now, there are 4 different conditions that relate enthalpy and entropy together, and it's in your booklet. Okay, I'm going to talk about that just now, about systems and surroundings. And that's where your change in entropy is either positive or negative. Okay? And then the delta H is the symbol we use for enthalpy. And I think you can see YH. I hope you click. Enthalpy is just a fancy word for heat. So this is the heat. Is heat energy being released or not? And this is entropy, which is the disorder. So if my delta H, if my change in enthalpy is negative, just from what you've learned before, is that an exothermic or endothermic reaction? So if you can remember from level 2, or if you've done the booklets recently, it's an exothermic. Energy is being given off, so it's negative because the particles are actually having less energy. That's why it's negative, because the energy is being dispersed elsewhere. Okay? If it's positive, it's an endothermic. In other words, the system is attracting energy into it, so the energy is increasing into the system. Here the energy is decreasing because it's all being given off, it's being thrown away. Here it's being grabbed in. So as an example of a spontaneous reaction, lighting a match, it burns, okay? It's what, exothermic or endothermic? A burning match. Exothermic. So energy is being released, so in the match itself is losing energy because it's being losing some of that energy stored in the bonds in terms of heat, light, and so on. So delta H is negative. Then the entropy, what do you think happens to the entropy? Will it increase or decrease? It'll increase. And the reason being is your solid atoms, well, your atoms in your solid match are now changing into carbon dioxide vapor, carbon particles, water vapor. So it's forming lots of gases, forming lots of particles, and so you've got a big increase in disorder. And so if you've got an exothermic reaction where there's an increase in entropy, that reaction is definitely going to work. Okay? If I have the opposite, so it's an endothermic, where it's trying to suck in energy from outside the reaction, from the surrounding air and so on, and if I've got increasing order or decreasing disorder, then that reaction is not going to work. Okay? That's not possible, theoretically. Okay, if I have something like ice melting, now you know ice melting is spontaneous. If you leave it out, you know, on your kitchen counter, it's going to melt. But if you were in the Antarctic, would the ice melt? I mean, assuming it's like minus 20 degrees. Would the ice melt? No. And the reason being is, remember what I said, your overall reaction must be, overall entropy must be positive. Now, if I've got ice, it's melting. So theoretically it's possible, because can you see my solid ice is breaking up into a liquid. There is more disorder, so that's why that's positive. But it won't happen at every temperature, because I need to get energy from somewhere to break those intermolecular forces of attraction. So here's a case where I've got an endothermic reaction, and with the endothermic reaction, I need enough energy from the surroundings to be able to put energy into the system in order to make the ice melt. So this is a case where the reaction could happen if the temperature is correct. So if you're in the middle of the Antarctic and it's minus 20, your ice will never melt. If you at home now in Wellington or somewhere in New Zealand, then it will melt. Okay? And here's the other case where again it's temperature dependent. This is where it's an exothermic reaction. So what I'm trying to show here is water vapor condensing. So I'm trying to show all this condensing over here. So if the water vapor is condensing, what can you tell me about the entropy? Is it becoming more positive or negative? Yes. There's more order when the water vapor condenses, and if it's more order, there's less disorder, so therefore less entropy. Okay. So again, you could make this reaction go if the temperature is correct. So this is what I want to say here. You've got to, whenever you're arguing whether a reaction is going to be spontaneous or not, because you're going to get a question in the exams about it, you need to think of the system. Okay, so the water vapor condensing, and then the surroundings, so the air around it. What is going to happen there? So for instance, water will condense, water vapor will condense, because what happens, as it condenses, energy is released. That energy is increasing the kinetic energy of the air particles, so they're speeding around more. So although there's more order in the water vapor, there's less order or more disorder in the surrounding air particles. So does that make sense, having the two? Looking at system, that's the entropy needs to be more ordered, okay, sorry, more disordered. It must be a positive change, and that's more disorder in order for a reaction to be spontaneous. And then I had this from your booklet, so this is the case where it'll always happen regardless, okay, because you're having energy being given off and more disorder coming in. This is where it'll never happen. This is where the two cases where it depends on the temperature. So this is talking about the ice. It won't happen in the Antarctic, but it will in your home. And again, think water vapor, well, you know, it only condenses at certain temperatures. If you were at 120 degrees, you know your water vapor wouldn't condense. Okay, so apologies about that. If you never see something being shared on the screen, just type and say, you're not sharing anything. Okay, so going to this now, what I just want to point out, and you do not have to do the calculation whatsoever, but is trying to see when are we going to get an increase in entropy or not. So take this reaction. I've got a solid, 2 solid particles mixing with 3 solid particles to form 3 gas particles and 4 solid particles. So I'm going from 5 solid particles to 4 solid particles plus 3 gas particles, do you think there will be more order or more disorder? Or let's do it a simpler way. Will delta S be negative or positive? Remember, if there's a positive change, there's more disorder. So I'm going from 5 solid particles to 4 solid particles plus 3 gas particles. Okay, it'll be, I think you're trying to do a plus there because you did an equal sign, yep. And you can see that over here, the delta S change for this reaction, can you see it's a very big number, very positive. So the more you change from a solid to a gas, the bigger the change. The more you change from fewer particles to more particles, the bigger the change. If I go to this one, I'm going from a solid and 2 gas particles to 1 gas particle. And this is not important at level 3, but it's a very symmetrical molecule, because disorder is also in how symmetrical or asymmetrical it is. So will it be a negative change or a positive change for entropy? It'll be a negative change because I'm becoming more ordered. Although I'm going from a solid to a gas, I'm also going from 2 gas particles to 1. Okay. Before I switch on to the next one, the N2 plus 2O2, who would like to guess, is it going to be a negative change or a positive change? Anybody want to have a go? It'll be a negative, it'll be more ordered because I'm going from 3 gas particles to 2 gas particles, and if I click on it you can see it's minus 121. Okay. The next one, I'm going from a solid to a solid and a gas, so I think you'll be able to see there's going to be more disorder, so it'll be a positive change. Good. And the last one, I've got an aqueous. Okay, Caleb, I'll answer that just now. I've got a aqueous system, which can be quite variable in terms of the disorder, but normally it means it's more disordered, and a solid, and I'm going to similar amount of aqueous, and I've got a liquid and a gas, so I think, you know, as Abigail's got there, it will be a positive change. Okay. If you've got a gas being formed where you didn't have it before, you are definitely got more disorder in the system. So it'll definitely be a positive change. Okay, so Caleb was asking what's delta G. Delta G is the way we work out those two quantities, the entropy and the enthalpy. It's called Gibbs free energy. That's why it's named after a chemist called Gibbs. And that's why it's delta G, G for Gibbs. As I say, you don't have to know that equation. But it does tell you if delta G is negative, then the reaction is theoretically possible at that temperature. So basically what you can do over here, I'm not going to mess around with it too much. This one is a very positive entropy, but it also needs lots of energy. So this is a case where you've got, remember those last two cases, positive entropy but also positive delta H, and so you can see at low temperatures it's not really going to work, and as you go to higher temperatures you've got a greater chance of it working. It's still not going to work, but now at this temperature it'll work. No, it's not something you need to know for level 3. I just was using this just so that you could see the delta S straight away by looking at these things. Okay, so I'm going to go back to this again. Right. Okay, so as I say, entropy is a dispersal of energy and matter. Oh, and I've got here, make sure, chemistry language is quite particular because if you use a capital letter or not, it can make a big difference. So make sure whenever you're writing S for entropy, then the S is a capital letter, because it can often be done in brackets or something like that, and we don't want you to confuse it with a small s for solid. So just be careful of that. So this is just in summary what we've been saying before. The more particles in the system, the more energy can be dispersed. So if we're going from solid particles stuck together to a gas, there's more dispersal of energy. Okay. The more energy the particles have, the more energy can be dispersed. So again, from going from solid to gas, the gas obviously has more energy than the solid. So or if you're even increasing in the temperature, there's going to be more energy, so the entropy would be more positive. And so this is what I've been saying there. Gases have more entropy. And basically, therefore, I'm saying the more disorder in the system, the greater the entropy. So if you had to explain why something was had an increase or decrease in entropy, you would be looking at the number of particle changes. You'd be looking, are we going from solid to gas, or gas to liquid, or that sort of thing. So you just need to work out, if you're going to a more ordered system, the entropy decreases. If we're going to a more disordered system, the entropy increases. So I'm saying in a solid, there's less entropy, liquid more entropy, gas even more entropy. Okay. We did it on the interactive, so I'm just going to very quickly go through this. 2 gas particles to 1, so it's going to be more ordered, so it'll be a negative change for entropy. Here, solid to a gas plus a solid, so it's going to be more disordered, a positive entropy change. 3 gas particles, because it's 2 of those, 1 of those, to 2 water molecules, so we're going from more to less, but we're also going from gas to liquid, so it's definitely going to be a negative change because we're going a lot more ordered. If we doing a vaporization, melting, so solid to liquid, then that's going to be more disordered, so it's a positive change. And from solid to aqueous, generally that's also a positive change. Why I say generally, sometimes I think for level 3 you just make it that it's a positive change. It's just sometimes the particles, when they disperse, they order the water molecules more around them, because remember, each ion is surrounded by water molecules, so there's order introduced there. But that's only for higher levels. Okay, so that's the answers, and hopefully you would have worked them out yourself. Okay, so remember what I said about the entropy and the enthalpy? The entropy with the systems and the surroundings. Take a cup of coffee. You know, if you've got a hot cup of coffee and you leave it on the table and you don't drink it and you forget about it, it's going to cool down. And if you think about if you're cooling it down, then the entropy is going to decrease because the particles will be moving more slowly in the coffee. But you know it's a spontaneous reaction because the coffee is going to cool down. And the reason being is, although the entropy decreases in the coffee, that heat is being radiated out from this high temperature in the coffee to the low temperature of the surroundings. And actually, the bigger the temperature gradient, the bigger the entropy effect, actually. So these particles are going to move around a lot more faster. So overall, the entropy has increased. So the entropy in the coffee has decreased, but if I take the coffee and the surrounding air, there's been an increase. Now, a few of you are typing, so I am keeping an eye to see if you've got any questions there. So just type in whenever you have a question. Right, so hopefully you get that idea of you need to explain the system and the surrounding, and to get a reaction to be spontaneous, you know, even theoretically, your delta H has to be positive overall. So be clear when you're writing about it that you've got to talk about the systems and the surrounding. Okay, so entropy of the surroundings is increasing, it's decreasing there, but there's more happening in the surroundings, so your coffee will cool down if you leave it. Okay, so here's an example from the 2014 exam. Sorry, I haven't had time to update this to last year's exam, but you get entropy pretty much every year. Here's an example where you dissolve Okay, no, you're just heating it, I think, from ammonium nitrate to form ammonia and nitric acid, well, or hydrogen nitrate, saying it's a gas. So what can you tell me? Is the entropy of the system increasing or decreasing? So you've got a choice of the entropy of the system increases or the entropy of the system decreases. That means what's happening inside, in this beaker and not what's surrounding it. Yep, so you're going from solid to gas, so it's definitely going to be increasing. Okay, now you think about the surroundings, and you're told it's an endothermic reaction, so it's sucking in energy from the surroundings. So will the entropy of the surroundings increase or decrease? Decrease. So if I'm taking energy away from it, the air particles are going to move more slowly. So that's going to be the answer. Okay. Then it carries on with the question. You've got to explain why it's spontaneous despite being endothermic. And so the things you'd have to talk about would be, you've got to spell out the obvious. You've got to show that you know an endothermic reaction has a positive delta H. You've got to spell out the obvious that a solid changing to liquid, or to aqueous, has got an increase in entropy. Okay, and why? You need to spell out this obvious, and this is normally an achieved level thing, this statement. So because you just rote learn it, delta S must be positive overall for the system for the reaction to be spontaneous. So that's like a rote learn thing. So that's always like an achieved level statement, but which you would also need for excellence and so on. And then you would talk about, a little bit more detail. Now, because I know we are running a little bit out of time, any questions on entropy and how we can work out whether the reaction is spontaneous or not? Do you think you all understand it? Okay, right. The other thing I just sort of try and squeeze in is the enthalpy definitions, because next week I want you to simply use these definitions. It's really important that you rote learn these definitions, that they're in your head, and I think there are Quizlets on it. I'll just check. So, because you need to know these definitions for both your intermolecular forces questions that we did last week, as well as for any calculations. So, there are 5 things you need to know. The first one is the heat of formation. If I say the heat of formation of water is so much, you must be able to write the equation for it. So what is the heat of formation? It's the energy released or required, so it could be negative or positive, and it's for the 1 mole of substance from its elements in the standard state. So when you write an equation, you are always going to have a number 1 here, okay? It can't be 2 or it can't be 3 or anything like that. If when you balance the equation you've got a 2 or a 3 there, you're going to have to divide the whole equation by 2 or 3 because we must have a 1 there. Okay, and we're only allowed to have 1 substance on this right hand side. So we're wanting to form just this. And it's from its substances in the standard states. So sulfur at atmospheric pressure and 25 degrees centigrade is a solid. Oxygen at atmospheric pressure and 25 degrees centigrade is a gas. So that's the way you would write it. Compare that to heat of reaction. This is a very general one. It's just for the reaction as given. So normally if you're not told anything else, you would just write a simple balanced equation and that's it. Okay? Or you would be using all the other definitions to work out the value of a heat of reaction, and they'll give you the reaction. Okay, so I could, for instance, use this one. This is not a heat of formation because I've got a 2 here. Okay, so my heat of reaction will be always for this as given. Notice my my units for a delta H, if I ever quote this, it'll always be mole, joules per mole. Whether we've got a 2 there or 3 there, it's always for the reaction as written. It's just a convention that we use. Heat of combustion, the delta CH, delta RH is for reaction, delta FH formation, delta CH combustion. This is going to be the other way around. Here we had to have a 1 over there. Now we've got to have a 1 for the substance we combust. So if I'm, for instance, using hexane and I'm burning hexane, I need a 1 over there. And can you see I've had to now use a fraction to make sure that I have a 1 over there. Normally we tell you don't use fractions in balancing. For thermochemistry, you definitely use fractions to fit the definitions. Okay, so again, you have 1 there, and a combustion is always reacting it with oxygen. That's the sort of definition. So this is also a combustion of sulfur, because I've got a 1 there, and I'm reacting it with oxygen, and those are my products. So sometimes the same equation can be fit different definitions. Okay, this would not be a combustion reaction, because although I've got a 1 there, I'm not reacting it with oxygen. Okay, and then basically we always use complete combustion. So if we're doing any carbon-based thing, it'll always be carbon dioxide and water. If there was hydrogen present, we would never go to the carbon or the carbon monoxide. Okay, and finally, very quickly, for the last 3 are the changes of state. So there's actually 6, not 5. Heat of fusion. Now, this is a difficult one simply because when you think of fusing, you think of, something fused, coming together and sticking together. But the heat of fusion is actually when it melts. So if you can just get that in your head, that it's a bit of an opposite to what you automatically think. So the heat of fusion is how much energy is needed to melt something. Okay, and it's always the same substance on the left and the right hand side. There's just a change in state from solid to liquid. Okay, solid to liquid, and it's always 1 mole of substance. Okay, so it's 1 mole going to 1 mole of the same substance. It's just a change from solid to liquid. Heat of vaporization, exactly the same, except I'm now going from liquid to gas. So at least this one makes sense. I'm vaporizing it, so I'm going from a liquid to a gas. And then the last one is the heat of sublimation, which I didn't actually put here. And sublimation is like carbon dioxide going from solid to gas. Okay. Right, and then I've just made a final point here is sometimes instead of giving them boiling points when you have to discuss intermolecular forces, they'll give you heats of fusion, because hopefully, or heats of vaporization. Because hopefully you can see that the bigger the value of this, the more energy is needed to separate the water molecules or the molecules of the substance. So a bigger heat of fusion or a bigger heat of vaporization means that those intermolecular forces are stronger. Okay, that's what I wanted to cover today, and I know I've rushed towards the end, and sorry for the stuff up in the beginning. Are there any questions with this?